So let me explain it to you one more time. See, in simple language, you have y, which is using linear regression, right? Which is a plus, let's say a1, let's say a naught. Okay, a naught, a1 x1, a2 x2 plus so on. So this is our linear regression equation, right? Now what we are using, we are applying sigmoid function on this, sigmoid of y. So the sigmoid function is itself is 1 by e power minus y. So I have to substitute this y here, 1 plus e power minus a naught plus a1 x1 plus a2 x2 and so on. So I'm just replacing y with these values, right? So what I was talking about was odds ratio. So let me not bring in odds ratio now, because odds ratio is a complicated topic. So let's not focus on this now, because this will anyways be covered in the future sessions. Okay, so let's not worry about this. Okay, it's just that you have to apply log and all. Let's keep it aside. Let's think in this way as of now, that this sigmoid function will give us the probability values, right? So the final probability is 1 by 1 plus e power minus a naught plus a1 x1 so on, right? Now what is a naught, a1, a2, h3? It's again, these are all again coefficients, right? So similar to linear regression, you have to derive, you have to come up with a naught, a1, a2 again, similar to linear regression, where we were trying to determine the m and b, the coefficients and the intercepts, using gradient descent method. Similar to that, here also we have to do the same thing. Okay, but I am not going into that detail, because that is anyways covered in the future advanced session. Okay, so it's very simple now to understand that. For example, let me take some x1, x2, x3, let's say y. Okay, let's say your y is whether your AC is split AC or window AC. Let's take your split AC is denoted as 1, window AC is denoted as 0. Now you have different input features. Input features could be the power, right? So let me take the power, I'm not sure. Let's take the power. And then what could be x2? Dimensions. Let's take the dimensions. What could be x3? Could you tell me what could be the basic difference between split AC and window AC? So what I was talking is, let's say x1 is your power, x2 is your dimensions of the AC. Let's say x3 is how efficient is your refrigerator based on maybe some other properties. You have some efficiencies, let's say, of your, not refrigerator, sorry, my bad, air conditioner. Okay, so by these three values, by these three inputs, we know whether our output is split AC or window AC, right? So we have to train our machine learning model on this data. And how our machine learning model is getting trained? Using logistic regression. We will train our model, our logistic regression, on this data. Okay, so once our logistic regression is trained, okay, with this historical data or the past data, so whenever we get a new data with some power, dimensions and the efficiencies value, what we will determine, we will predict the probability value. So if the probability is 0.5, less than or equal to 0.5, then it is considered to be 0. If it is greater than 0.5, then it's considered to be 1, class 0 and class 1. So the output what you will get from the logistic regression will be the probability values. Based on the probability value, it will be identified as whether it is 0 or 1. Okay, so If the output of this logistic regression is, say, the probability value is, say, 0.1, then you can tell that the output, the prediction for this new data which is coming in, the AC would be window AC. I'm just giving you some examples, okay? So, okay, with this power and dimensions and efficiency, if some client comes to you and asks what kind of AC we should manufacture, then you should tell that we should manufacture window AC because we have a lot of different window ACs with the same configurations, and that would be easy to put in the market. In this case, it is telling you the probability of split AC, probability of Y output is equal to 1, probability of output being 1. Okay, so higher the probability value, consider that it is class 1. Lower the probability value, it is considered as class 0. Okay, again, I just wanted to tell you that there will be a separate loss function for this. It's not the same loss function as we have in linear regression. If you want to explore, you can do that, but or else you can wait for the advanced course for this. Okay, so now there is one simple example which I have taken here. Okay, so it's pretty straightforward. You have a data set with age, different people with different age, and whether the person is married or not married. Simple. So this is a binary problem. Why is it binary problem? Because the output has only two classes, 0 or 1. Class 0 is considered as not married in this case. Class 1 is considered as married, right? So now if you have more than two classes, how will you work? See, Python will work for you. It's okay. You can directly implement. If you have more than two classes also, Python will work for you. But there is a separate logic which is called as multinomial regression, where there will be a slightly separate logic. It's just an extension of this logistic regression. You will have three classes, say 0, 1 and 2, and then there is a just slight extension of this logistic regression. So you have to explore about that, or else maybe we can discuss that in the future sessions. Okay, but for time being, for logistic regression, where you have only binary classification, whether it is binary or multinomial, Python will do it easily for you. Same code, you have to just write same code. And for mathematics, you have to do some extension on that. There will be a slightly extended mathematics on that. Okay, so if you notice, for the age of a person, if it is 25, 26, 27, 28, then the person is not married. And it's slightly logical also, right? See, in this case, the data is very small. I'm able to interpret directly. But if the data is huge, then you have to do descriptive analytics, right? Exploratory data analysis. Then only you can understand whether the data is making sense or not, right? So for that, now I'm just doing it directly because the data is very small. Lesser age considered to be a not married. With the age around like 30, greater than 30, married, which also makes sense, right? As per current era. So if you plot that on the graph, it will look something like this, right? Now, there is a new data which comes in, for example. So this is very important, okay? Now what we are trying to predict is the probability value will give you whether the person is married, okay? We always predict in logistic regression, we always predict whether the probability of y is equal to 1. We are trying to predict the probability for y is equal to 1. Y is output. So if the probability value is greater than 0.5, then it's straightforward, person is married. If it is less than 0.5, the person is not married. Now you must be thinking, where is this magic number coming in? Why the threshold value is 0.5? Why it is so important? Now you have to understand, to explain this, it will again, I'll just try to give you some hint here. Let's do some analysis here. Now let's take an example. Okay, now it's very important, guys. It's very important. Try to understand this. Its name itself is confusion matrix. Okay, its name itself is confusion matrix. This looks something like this. For a binary logistic regression problem, it will look something like this. So let's say this is your actual, this is your predictions. Now let's say whether the person, we have to predict, say for example, let's take one more example of say x1, x2, x3 and y. There will be multiple inputs. Okay, x1 denotes the age of a person. Okay, x2 denotes salary of a person. Okay, x3 denotes the gender of a person. Okay, now y is to predict whether a person has car or no. Now say you have 100 data points which you have splitted into training data set and test data set. Okay, say in training you have 70 data points, in test you have 30 data points. Now say this is your actual ones, your actual zeros, predicted ones, predicted zeros. So in linear regression, how did we predict the accuracy? Using R square, right? In logistic regression, how do we predict the accuracy? Simple, it's by how well we are predicting the output, right? That means, let me rephrase my question by using this confusion matrix. Okay, this is very important, guys. It will be your interview question. So for example, okay, on this 70 data points I have built a logistic regression. Okay, and in this 70, say I have 40 ones and 30 zeros. In this 30 test cases, say in 20 I have ones, in 10 I have zeros, right? So let's take this. So what do we think? If we are actual, in actual if it is 40 ones, we assume that we should also predict 40, predicted ones should be also 40, right? If the actuals are 0, the predicted ones should also be zeros, right? So I am creating a confusion matrix for only training data set. Okay, 30. Okay, now can it happen? See, it's very rare that you get 100% accuracy. It's very difficult to achieve this, right? In real life, what you will notice is this. Say the actuals are total are 40 for ones, for zeros it is 30. Now the actuals are ones and the predicted are also ones, which are say 30. That means ones are correctly classified as ones, right? Say some of the ones are incorrectly classified as 0, because it's very rare to get 100% accuracy in a real life project. Now out of 30 zeros, whether the person has a car or not, so whether say 30 people were not having car in the training data set, say we have predicted correctly for 25 and for 5 we have incorrectly predicted. Now could you please tell me what could be the accuracy for this training data set? Simple, common sense. Can you tell me what could be the accuracy for this model? How is it 75%? So no, it's not 30 by 40, but you have, it's good that you understood that. So you are just telling the accuracy for only ones, but accuracy will be based on the classification of 1 and 0 both, right? So how many are correctly classified? 30 plus 25 divided by the number of data set in the training, which was 70. So it was 55 divided by 70, right? So now you should remember these terminologies. It will always be there in your lifetime if you want to become a data scientist. A 1 is always considered as a positive case. So actual 1, predicted is also 1, is called as true positives. Actual zeros, predicted as zeros, are called as true negatives. Okay. Actual 0 predicted as 1 is false positive. Actual ones predicted as 0 is false negative. So the accuracy formula is true positive plus true negative divided by true positives plus false positive plus false negative plus true negative. It's very simple to understand, but You have to remember these terminologies because in interview they might ask what is true negative. You have to tell that negative events or just say that the events which are of class 0 are correctly classified as 0, right? So what are false positive? So the ones which are incorrectly classified as positive events. What are false negatives? The events which are incorrectly classified as negative events, right? So as the class progresses, you will understand which is severe. See, for us, we have to minimize Fn false negative and false positives, right? We have to minimize this. It's our objective, right? Our ultimate goal should be, our accuracy should be high and false negative and false positive should be as low as possible. But as the class progresses, as the session goes on, once you complete this course, you will come to know it's not every time that accuracy is important. You might have to look for false negative or false positive also. For example, in this case, let me give you one simple example. See, it's good that if we can minimize false negative and false positive, but we should know which one we have to minimize more, okay? And how to minimize that we'll look into later. But now what we are discussing is which one should be minimized. That's important. Let's take an example which is of a clinical trial. For clinical trial, the accuracy should be very good, right? Say now our confusion matrix. Say this is malignant cancer which is considered to be 1, let's say, and this is this is your benign cancer considered as 1 and malignant cancer which is considered to be 0. Okay, now for this example, say you all understand this benign cancer and the malignant cancer, right? Malignant cancer is the one which is more harmful. Say if I have here say 10 and here I have say 20, okay? With one of the logistic regressions or one of the classification problem, I got this as 10 and this as 20. You understood it, right? 1, 0. So false positive as 10, false negative as 20. Now let me give you one more example of same clinical trial. Same benign and malignant. Say this is 20. Say this is 10. Say this is case A, this is case B. In case A, we have used say logistic regression. In case B, we have used some other classification algorithm. Let's not name it now because you have not learned it. Let's say it's some other algorithm. Now tell me which is more severe here. Leave it about true positives and true negative. Tell me which is more severe in this case. See, the point is here, say malignant cancer people are predicted as benign cancer, right? That means, see, first of all, it's important. The one which is more harmful is predicted as less harmful. Say here in this case, the benign cancer is predicted as malignant cancer. That means the less harmful cancer is predicted as more harmful cancer. So that's okay. What the doctor will do? Doctor will do the separate checkup, all the different tests for all these people, 20 people. But for these 10 people who were predicted as less harmful cancer, like what happens in a clinical trial, what they would understand that what they would think is this 10 people has less harmful cancer, right? But in case B, there are 20 such people who are having a malignant cancer but as predicted as benign cancer. So case B is more severe, right? So for this case, false positive is the one which is of important criteria which we have to minimize, right? Otherwise, if doctor goes with the prediction, they might not do the separate different test for this 10 people. And then you know what could be the end result, right? So which is wrong. So here the objective is to minimize the false positive rather than increasing the accuracy. The important thing is to reduce the false positive. Okay, it's okay if we have more false negative for this example, right? If we have more false negative, it's okay, because then doctor will be extra conscious on those patients. That's it. And they will do extra test. It's just a matter that they might have to spend a lot of extra money, but they at least they would not lose the life, right? It's a matter of life here, right? So it's important that we should understand for which kind of problem which parameter is very important. Is it true positive? Is it accuracy? Is it false positive? Is it false negative? Did I clear some fundas by taking this example, guys? For our engineer examples, it's very simple. So why will there be error again in the training data set? Right. So see, for example, this is your training data set. Okay, let me give you one example. There would not be, for simple problems, if you do it manually, you are doing a classification of whether a person has a malignant cancer or benign cancer using manually by looking at all the reports and different stages you're looking at, and then you understood that manually doing it by a specialist doctor, the error is 0%, right? But when we are making our machine to learn this using algorithm, okay, then it's not necessary that you will get a 0% error. 0% error is your very optimal result, right? It's your base by which you will compare. But machine cannot get accuracy of 100%, right? Because it's a machine, right? We will always try to achieve this accuracy towards 100% and or the error to 0%. We will always try to do that, but it's not possible. Okay, let's take for example, okay, say in this case, say there is one more person, say of the age 24, let's say of the age 24, okay, and say the person is married. Now when we train the model, 24 will be somewhere here, agreed? 24 would lie somewhere here, right? I'm just plotting it. So 24 would be somewhere here. So by looking at this graph, we can assume that this person will not be married. There can always be extreme cases, right? So for which it is very difficult to predict. Those cases will always improve the error percentage. See, manually you can always think the error would be 0%. But in some cases also, believe me, manually also you cannot achieve 0%. Okay. So by this example, I'm just trying to tell that it's not necessary for the training data set you will get an accuracy of 100%. You will always try to bring the accuracy to 100%, but it's very difficult. Okay. You always try to achieve a better results for training data set. So for example, you apply some algorithm, say A, you got some training accuracy, say 90%. With algorithm B, in the training accuracy, you got 95%. Then what you would do is, you would test this on the test data set also. If the similar pattern is observed on the test data set as well, then see, in our case, both training data set and the test data set are historical data, right? We are just for our analysis, we are splitting test and training data set. Okay. So if we are looking at the same pattern for both training and test data set, then what we tell in the future, for example, in the future, if we get any data, then we will use algorithm B. Then we will go with algorithm B. Okay. So to give you one more example, okay, you have a training data set. X is, say, whether it is a, in X you have images. In Y, our output is whether it is cat or dog. Suppose you got the data set with 100 images. Okay, you got let's say you got this data set, image 1, image 2, image 3, and so on. Say this is cat, this is cat, this is dog, this is cat, so on, right? See, in this data set we already have the labels. Okay, what we are doing randomly, using random sampling, we are taking 70% of the data as a training data set. Now in training data set you have, say, some 70 images. Okay, these 70 images will look at its output. Okay, see, we already have the outputs here, so that's the reason we are calling it as supervised learning, right? So it will look at this output. Okay, the algorithm will be built on this training data set. Okay, based on that it will predict. Now once the algorithm is built based on this output labels, first it will predict for the training data sets also, right? Say for 69 images, or let's say for in actual case, in actual results, we already have 100% accuracy because we have already labeled them. But our algorithm is built based on looking at the actual results. So it will, let's say it has predicted well for all the 70 images except for one. The reason could be blurry image. So for a blurry image, imagine it, it's very important. Okay, let's imagine that you have a blurry image. For a blurry image, for a human being is very difficult to identify whether it is a cat or dog. It's just that you got, in actual, you have labeled it with the help of some, say, animal lover. Okay, with the help of some animal lover you have labeled all the images correctly. But if there are some blurry images, just imagine if a normal human being is able to distinguish whether it is a cat or dog, how will a machine distinguish it? Your algorithm is built on training data set. How? By looking your output labels. With those output labels, the algorithm is built. Now, once the algorithm is built, we are now implementing the same algorithm on training data set first to understand whether our algorithm is able to predict well or not for training data set itself. Okay, say, let me give you one simple example, very simple examples. Let's say you have 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Say you have ones, something like this. I'm just trying to give you one example here. Okay, now you have 1 0 here. Okay, concentrate, it's very important. Now if I want to distinguish these two classes by a single line, how will I do this? By this single line. So I have built an algorithm which differentiates these two classes. Now if you notice, for this extreme cases, this is incorrectly classified. Now to make it correctly classify, what should I do? Say I have 0 0 0, 1 1 1 and 1 0 here. Then the classification should look like, then I should classify like this curve, right? I should use curve, right? Exactly. Now, so what happens while doing this? So this is important. Okay, we have tried to increase the accuracy for training data set, and the algorithm which we have used with this, it will have different characteristic, and this algorithm will have different characteristics. Both the algorithms will have different characteristics, right? Now there might be a training data set accuracy, say the training accuracy is say 90% with algorithm A. Here the training data set has an accuracy of say 100% with algorithm B. Okay, Now we have to implement this on test data set. You don't worry about the curve based regression now. Okay, anyways we will be looking at curve thing by using different algorithms, but don't worry about the polynomial regression that you can always use. Okay, but I'm not teaching that in this course. The other curve classification type which we will be learning are different in this course. Okay, so don't worry about that. But let's take curve to explain you in a better way. Let's take curve only.